Hi, everyone, and welcome to online lecture 12. This is the lecture on chi-square, and we're actually going to talk about two different kinds of chi-square. And then just in closing, we'll talk about some other extensions of regression. So I know we're going to kind of go backwards and talk about that, but you'll see why I'm doing it when we get there. Okay, so first off, in terms of practice problems, I offer a couple of optional practice problems for you, and I'll get those posted for you so you can take a look and see if you want to do them. You don't have to submit them. I'm going to provide you output so you can check your work. So it'll be two problems, both A and B. Now, if you feel you need to see a write-up from me, let's talk about that in class. But my goal is to provide you the output, and we'll see if the write-ups from Laird is sufficient. Okay. So let's go back to the beginning and talk about kinds of variables. There are nominal or qualitative variables. Those are the ones that have few values, usually names or categories, and no natural order. These are things like gender, race, political party, religious affiliation, eye color or color preference. Any of those would be nominal or qualitative variables. Okay. Ordinal, interval, ratio, quantitative, or continuous variables. These are all our numeric variables that have many values, are represented by numbers, and do have a natural order. What order did you finish in the race? First, second, third, fourth, 100th? What temperature is it today? Is it 60 degrees or 70 degrees or 40 degrees Fahrenheit? Or how old are you? Or how much time did it take a person to complete a particular task? All those are numeric variables. Okay. So this is a nice way of reviewing the tests that we've used so far. When we've talked about t-tests, the Mann-Whitney U-test, the Wilcoxon test, the one-way ANOVA, the Kruskal-Wallis, the repeated measures ANOVA, the Friedman, the factorial ANOVA, these were all quantitative. One quantitative variable, one continuous variable. Okay, so that had at least one quantitative variable. At least one quantitative variable. Then we talked about correlation and different types of correlation and simple linear regression, and these had two quantitative continuous variables. And when we talked about things like ANCOVA and MANOVA and MANCOVA and multiple regression, we had two or more quantitative continuous variables. Okay, so we had one, we had two, we had potentially more than two. And now it's time for something completely different. Now, as we close our semester together, we're going to talk about the chi-square, which is when you have no quantitative variables, zero quantitative variables. So we're not going to have our usual parametric assumptions that we're going to worry about, right? We worried a lot in the past if our population was normally distributed and if our sample was normally distributed, and we are not going to worry about that anymore. We're going to use a non-parametric or distribution-free statistic. Now, we have used some of those non-parametric statistics so far, right? I'm sure you recall that we've used the Mann-Whitney U, and we used the Friedman and a host of others, Kruskal-Wallis, etc. But this one is special because it has no quantitative variables involved. Okay. So With chi-square, there's two different kind of situations, and we're going to talk about both. The first kind is when you have one qualitative variable, that's it, and you want to compare which group people are most likely to belong to. This is often called the chi-square test for goodness of fit. And an example would be, are volunteers for psychology experiments more likely to be male or female? And we could add a third category to this, that would be no problem, or non-binary, or a fourth category, or a fifth category. But we only have one variable. In the other situation, we have two qualitative variables, and we want to know if they are independent of each other. This one is called the chi-square test for independence. And it can be a 2 by 2, row by column, or in R by C, row by column. In other words, I could have a 3 by 5, a 4 by 8, whatever I like, but it's two variables. So again, let's take our gender. Is gender independent of disorder diagnosed? That's a fun one. Now we'll start off with just two genders. We'll just start off with male and female, independent of disorder diagnosed. And we could contrast histrionic personality disorder and antisocial personality disorder. And we know that antisocial is diagnosed more in males than females, and we know that histrionic tends to be more diagnosed in females than males. So that would be kind of an interesting little analysis to look at. Now, let's change this a little bit. Let's say is gender with 3 categories this time, just for fun. And we'll do male, female, non-binary, independent of disorder diagnosed. And this time we can expand our diagnoses, and we could look at different ones, right? We can look at major depressive disorder, PTSD, and we'll put in narcissistic personality disorder. Okay. And we could look across those disorders and see if some are more likely to be diagnosed than others. In other words, you know, and then we could question, of course, if there's a true difference or if there is a bias in that, but that's a question for probably a different course in another day. But anyhow, that's the idea. You could have more than 2 categories in your row. You can have more than 2 categories in your column, but again, only 2 variables total. Okay. All right. So let's start with the first situation, the chi-square test for goodness of fit. Are people more likely to belong to one group than another? And just speaking in super generic terms, we could say our alternative hypothesis is people are more likely to belong to certain groups or categories. Our null, people are not more likely to belong to certain groups or categories. So let's talk about the distribution of eye color for a sample. And our sample has an N of 40. And if we look at our observed frequencies, and I'm going to start using this terminology more as we talk about chi-square, observed frequencies, we see that in our sample of 40, we found 12 people who reported blue eyes, 21 who reported brown eyes, 3 green, and 4 other. Okay. So in a sample of data, individuals in each category are counted, and those counts are the observed frequencies, just like I was sharing with you on the previous slide. Now, the expected frequency, that's the frequency value that is predicted from the null hypothesis in the sample size. The expected frequency is the total N times the proportion expected for each cell. Now, this would be a little bit easier if the proportion expected for each cell was even, right? Let's say we expected an equal number of people to have blue eyes, brown eyes, green eyes, other eyes. then we could say our total N of 40 times the proportion expected for each cell. Well, that would be 25% or 0.25. So if we took 40 times 0.25, we would get 10 for each of those. 10 for brown, 10 for blue, 10 for green, 10 for other, right? Because 40 divided by, or take 0.25 times 40 or 40 divided by 4, however you want to think about it. Either way, you're going to get 10. Okay. But what if you know something about genetics and eye color, and you know that brown is much more common in the population than blue, let's say. You might say, well, I would expect that in a general population sample, I would see that 50% of people have brown eyes, 20% have blue eyes, 15% have green eyes, and 15% have other colored eyes. Just for fun, okay? That's probably way off because I don't know my genetics too well, but you get the idea. And then we would take our total N, 40, for brown times 0.50. Now we'd expect 20 people to have brown eyes. And we would take our 40 times 0.20. We would expect 8 people to have blue eyes. And we'd go on from there. Okay, all right. And so expected frequencies, if you're starting to wonder, they don't have to be whole numbers. Even though I know we're talking about counts of people, expected frequencies can work out to be in decimals. Okay. So now that we talked about that piece, let's get into our assumptions. First assumption, you have 2 categorical variables. Well, we already talked about that, right? A categorical variable can technically be either nominal or ordinal. Now, I know I emphasized nominal before, because even if you use an ordinal variable, you've got to treat it as nominal. In fact, the truth is, if you have an ordinal variable, this really isn't your best choice, in my opinion. Unless it's some weird situation where you really think your ordinal should be treated as a nominal, no, I wouldn't recommend this, okay? Second, you should have independence of observations. Persons' cases cannot be in more than one group, okay? So if someone says, I have blue-green eyes, nope, that doesn't quite work. You can put them in the other category if you like, but don't put them in both blue and green. Okay, you got to have independence there. You can't have people overlapping. And then finally, the only one we really have to check is that all cells should have expected counts greater than 5. Okay, so that expected frequency thing we were just talking about, we want them to be higher than 5 for each of our cells. Okay. All right, and then we have chi-squares aren't for continuous data. Challenge accepted. All right. So to go through and understand this a little bit more, I want to go through an example. This is an example about an abstract art painting, and this study was done by someone named Fielding. And Fielding asks, which way is up? Fielding believes that one or more orientations of this painting will be preferred. In other words, since it's abstract art, technically any one of the 4 sides could be placed up. Okay. So alternative, there is a preference for one or more orientations of the painting. No, there is not a preference for orientation of the painting. Okay. Okay, so we see here that we have the actual data, the observed frequencies, and we have 50 people total that were sampled. 18 said top up correct, 17 said bottom up correct, 7 said left side, 8 said right side. So again, since we said that, you know, the null was that there would be no preference, that means they all should be equal, right? So this is our null right here that we're figuring out. 50 times 0.25, or 50 divided by 4, would give you 12.5. Okay. So the expected frequency, again, is the frequency value that's predicted from the null hypothesis and the sample size. Okay. And that's a piece worth understanding, just so you have a sense for it. Okay. All right. So I am just going to show you the equation for the chi-square test for a couple of reasons. One, it's one that's relatively straightforward to understand, and I think it's helpful to look at it and view it when you're going forward. But I don't expect you to be able to utilize this particular formula. Okay, but we'll talk about it for just a moment. So chi-square, you're familiar with this term, is the lower case Greek letter chi with a square attached to it. O or FO is the observed frequency. E or FE is the expected frequency. So our chi-square statistic is you take each observed minus expected and you square it and you divide that by expected. You do that for all the cells and then you add that number up, and that's simply your chi-square. So let me say that one more time for the curious. You take your observed frequency minus your expected frequency, square it, and then you divide by your expected frequency for that cell. And then you repeat for the next cell, for the next cell, for the next cell, however many cells you have, and you add those up. Okay. And the idea is that we're not going to reject the null if the discrepancy between the observed and expected values is small, but we will reject if the discrepancy between the observed and expected values is large, right? That's what we're looking for, a big difference between observed and expected. Okay. So all chi-square values are greater than or equal to 0. That's nice. This is always positive. It's positively skewed. And there are different distributions depending on the DF. We've dealt with that before. Now, the degrees of freedom for the goodness of fit test is always the number of categories minus 1. 4 categories, 3 degrees of freedom. And again, while I won't ask you to calculate the degrees of freedom per se, it's good to know, it's handy because you know, it's good to be able to look at your output and understand and know that it's actually representing what you intended it to represent. Okay. Okay, we already talked about that. Sorry, I went the wrong way. Okay, chi-square distribution in the critical region. Okay, so this is just, I just wanted to show you a picture of how the critical region looks for this kind of data. A little bit different from when we were back looking at Z and T, where the cutoff was on both sides. Really, the cutoff is just on one side here. And you can see how different that chi-square looks for different values of DF, for different number of categories. So the more categories you have, the more it starts being a little bit less skewed. Okay. Just like anything else we've really talked about, the critical value for the chi-square is located in a table based on the degrees of freedom and alpha. But again, we don't really use tables in this class. We primarily look to SPSS, but that is how it works. SPSS is looking up the table for us in the background. Okay. So if the calculations were actually done for our little art example here, we would get a chi-square of 8.08 and a DF of 3. I won't go through the chi-square, but I will say that the 3 comes from 4 categories, right? Minus 1, 3. Okay. Now let's go to SPSS, what we're actually focused on, interested in. And here we see the observed ends given to us just like this, the expected ends, and a residual, the difference between these two. Okay. We get our chi-square, 8.080. We get our degrees of freedom, and we get our p-value. This is what we like. 0.044, less than our alpha of 0.05. I'm just pretending our alpha is 0.05, less than our alpha of 0.05, so we can reject the null. The distribution of eye color was not even across the categories. Okay, and we see that 0 cells have expected frequencies less than 5. The minimum expected cell frequency is 12.5. As we saw in the previous slide, right? These were all 12.5, nothing less than 5. Okay. So that's how you check that last assumption there, just by looking there. Okay. So now let's go to layered. Let's go through a layered example, and then we'll come back, talk a little bit about the next chi-square, and do layered again. Okay, so I'm going to escape out of this. And I'm going to have to do it this way, I think. So I'm just sharing the wrong one with you right now until I get over to layered. Okay. I'm just making sure I'm in the right place. Perfect. Great. Okay. So I started here actually on purpose rather than in the chi-square test. And I'll show you why. There's a whole bunch of chi-square tests in layered, so I don't want you to get confused. You'll notice there's 2 down here, chi-square test for homogeneity. There's 2 of those. There's a chi-square here for association, a chi-square here for independence, and the one we're interested in for right now is right here, middle column under 1 sample, chi-square goodness of fit test. Okay, so again, it's right here, middle, almost like the middle of the whole thing, but middle row under 1 sample. Okay, here we go. Okay, so let's start off. We already really talked about the background and requirements. So let's start off with our example for this particular setup. A researcher wants to recruit 100 participants to a study that will investigate the effect of an exercise training program on health. These individuals can either be normal, overweight, or obese, the 3 main categories of the categorical variable body composition. The researcher would like to determine if participants' recruitment to the study leads to an equal number of normal, overweight, and obese participants choosing to participate. In addition, the researcher would like to understand whether the number of normal, overweight, or obese participants follows the same proportion as that in the population, where it's known that 50% are normal weight, 35% are overweight, and 15% are obese. Okay, so what are we setting up here? We're setting up first a goodness of fit where we can look for equal numbers across our categories for an expected count, and then unequal, right? Based on the 50, the 35, and the 15. So we'll work through each of those. Okay. Here is a setup of the study. Now, there is something a little bit different about chi-square, and I want to go through this with you. You could set it up like on the left, where for each person, each of the 100 people, you have a body composition. I assume they have their toe tag actually selected, and this is really like a 1, a 2, a 3, a 3, a 1, a 2. You get the idea. And you can enter all that data. But here's something cool about chi-square. You don't have to. All you need are your frequencies. So you could enter normal, that's 1 category, and there are 51. Overweight, 28, obese, 21. And you could be done right there. There's just one more step you'd have to take. But you don't have to go through and enter all 100 data points. So that is super handy. Okay, and I'm going to show you how this is done. Okay. So if you have the individual scores, here's your variable view, the body composition. You have the 1, 2, and 3 for normal, overweight, obese. You're used to that. It's a nominal measure. For a role, they're suggesting you select none. Okay, remember roll all the way to the right here, none. So I would go ahead and do that. Again, I'm not a big user of the roll feature, but I think that makes sense. Go ahead and select none. And here's your data view, just like we saw on the previous page. Now, let's look at it with the frequency count data. So remember, this is if we do it the other way. We put in our body composition variable, all right, with the 1, 2, 3. We put in our frequencies. One, two, three, same thing. But now, when we look at it, first of all, our frequency is a scale variable. I should point that out. I don't think it makes a huge difference, but I would go ahead and list it as scale. Okay, roll for both can be none. And now your data just looks like this. Okay. So here's the thing. We have to tell SPSS that that really represents 51 people, right? The normal really represents 51 people, and so on and so forth. So here's how you do it. You go under data, go all the way towards, I was going to say to the bottom, and then I'm realizing we have slightly different people using slightly different versions of SPSS, so it's definitely toward the bottom, if not exactly at the bottom. You're going down to weight cases. And then you're going to weight cases by frequency. So I'll show you this. Here we go. Weight cases by frequency. And then you hit OK. That's all you have to do. Saved you a lot of data entry headaches, potential data entry errors, and now your data set is complete. Okay. So now let's look at our procedure. We go to Analyze, Non-Parametric Tests, Legacy Dialogues, chi-square. Again, that's non-parametric tests, legacy dialogues, chi-square. There is technically another way to run this, but I'm not even going to go there. I'm just going to let you guys, unless you want to, then we can talk about it, but I'm just going to leave you with this way of doing it. This is a perfectly fine way of doing it. And then you have your chi-square test that pops up. You bring over body composition. Now, I do want to point out, yeah, and if you actually had weighted your data, you would still see the freak there for frequencies, and you would just bring over body composition and leave frequency behind. Okay, that's the only one you need. Now, I do want to point out that the default here is that all the categories are equal for your expected values. This is where we can change that. Now, we're not going to at first, but I'm going to show you in a minute or two how you can do that. Okay, but for now, that's all you have to do. Start over your body composition, hit OK, and you're off to the races. Okay, now let's look at unequal proportions. Remember that we were talking about the 50, the 35, those percentages that we were told about. Okay, so same thing so far, non-parametric, legacy, chi-square. We're going to bring over our body composition, either leaving behind freak or not, depending on whether we had that there. And now we click off the values, and we're going to enter in the values. So here's the important thing. Your value order that you're going to enter in needs to match what your value order is in your data. In other words, if you made 1 normal, 2 overweight, 3 obese, then the first number should be for normal, then overweight, then obese. Okay, it's got to match. So it's really important to have value labels here. And it's really important to remember or look back what they are. That's fine. And then just go ahead and match it. Okay. All right. So that's what they're explaining here, is that body composition, the first value we enter is 50 for the normal. And that's got to match this, 50 for normal. Then 35 for the overweight. And then, what was it, 15? 15 for the obese. That's how you do that, okay? So it's value add, value add, value add. Okay, all right. That's how you deal with unequal proportions. All right. Here are the assumptions that we go through, which is really the only thing we're checking here is if we have any cells that have expected frequencies less than 5, and thankfully we do not. You can see we have 33, 33, 33 for our expected ends. This again is the equal proportion one. I'll show you the unequal proportion one in a minute, although it's out of 100, so I'm betting you can guess what that's going to look like. Okay, so let's look at this result. We get a nice high chi-square, df of 2. Why? Because there were 3 categories. And our p-value is 0.001. Great. Significant, right? Less than 0.05 for sure. It is significant. Okay. Now, unequal proportions. This time, our expected ends are 50, 35, 15. Again, there are 0 cells that have expected frequencies less than 5. The minimum expected cell frequency is 15, which is right here. Right? That's our 15. Now, let's look at the test statistic. This time, it's 3.820. DF of 2 is the same. That makes sense. And our significance level is 0.148. Now, that's bigger than 0.05, so we're not going to reject. So why is it that we rejected before and do not reject now? This is worth a moment of our time. So here, look at these differences. Look at the residuals. That's the easiest way to do it, right? 17 and 5 and 12. Whereas down here, the residuals are much smaller, just 1, 7, and 6. That's why. The differences between the observed and expected are much smaller down here than it is up here. Okay. All right. Now, the best way of dealing with a violation of the expected frequency assumption, in my opinion, is to run an exact chi-square goodness of fit test. However, this is not easily done with SPSS. So, I'm trying to, so if you fail and you want to, you could collapse some categories. That's always an option, right? If you decide that certain categories can be collapsed, you can collapse them. But another option that they offer is to proceed with caution. So I will tell you, if this was for your dissertation, I would certainly look into a little bit further how to do that exact test, or look into whether you can actually collapse some categories. Sometimes people do that. If it's not critical to what they're studying, it all depends. But for the purposes of this class, I will tell you to just proceed with caution. Okay, So for this class, you'll proceed with caution if that happens. Okay. In terms of interpreting results, we're actually going to move past this. Again, it's just showing you how the observed and expected and residuals look for your for when it's equal proportions. Now, here's the thing to look out for. If you forgot to weight your data, this is what it's going to look like. You'll have observed ends of ones. That's really the main thing. Don't even worry about what your expected ends look like. Your observed ends will be all ones. Okay. That's a big hint. I forgot to weight my data. Let's go back and do that. Okay. Okay. So in terms of expected frequencies, we talked about where those come from. So you have a little bit of an understanding of that. This is just a little bit of a more explanation of how they took the 100 divided by 3 and got 33.3. Okay. Okay, and these are, this is a little bit more explanation of the residuals and your model fit. Okay. And this is just going through and showing you, just like I was talking about with you guys, how to actually calculate the chi-square. So again, if that's interesting to you, you can look further at that. Here are your observed and expected frequencies for the unequal, just like we were talking about. Again, big warning sign, if you get all ones, you forgot to weight your data, unless you really have an N of 3, which is highly unlikely, right? Okay. All right. All right. So now we're talking a little bit about model fit again, and we can just see where that residual comes from, right? Okay. So same basic idea here. And then we can finally get into reporting for equal proportions. Let me switch this over to APA. Now, there's 2 options here, and there's really only one sentence that's different between the 2 options. And I'll show you. The chi-square goodness of fit test indicated that the 3 body composition types were not equally represented by participants recruited to the study, and then it gives the chi-square. Here, the chi-square goodness of fit test indicated that the number of normal, overweight, and obese participants recruited to the study was statistically significantly different. And then it goes on the same way, with just over half the participants having a normal body composition. Okay. Either's acceptable. I like the second better. I do. And it's just honestly, I think, a little bit of personal preference here. But either's perfectly fine. Yeah. I like to talk about statistically significant different things. I think that just is keeping in the language we've been talking all along, keeping with that kind of language. And so I think it's a little bit easier, but that's up to you. Okay. And then this goes on to give you an example if it's not significant. So the first 2 are equal proportions if it is significant. The second 2 are equal proportions if it's not significant. And as you can see, it's very, very similar. Okay. I'll read one of these through for you, I guess. We might as well, right? Of the 100 participants recruited to the study, 51 had normal body composition, 28 were overweight, and 21 were obese. A chi-square goodness of fit test was conducted to determine whether an equal number of participants from each of the 3 body composition types were recruited to the study. The minimum expected frequency was 33. Nice to put that in. The chi-square goodness of fit test indicated that the number of normal, overweight, and obese participants recruited to the study was statistically significantly different, with just over half of the participants having a normal body composition. So they're reporting the observed frequency here, right? Okay. All right, so now let's talk about reporting for unequal proportions. And I'll switch over to APA again. Again, this is the same pattern here. I'm going to go down and talk about a significant one. So I'll use this one right here. Of the 100 participants recruited to the study, 51 had normal body composition, 28 were overweight, and 21 were obese. A chi-square goodness of fit test was conducted to determine whether the participants recruited to the study had the same proportion of body types as those in the general population. The minimum expected frequency was 15. The chi-square goodness of fit test indicated that the number of normal, overweight, and obese participants recruited in the study, or recruited to the study, was statistically significantly different from the proportions found in the population. Okay. All right. So I should have mentioned, this is talking about the proportions not being equal for expected frequencies, not significant, proportions not being equal, significant. So you have all four right here. All your choices right here, I should say. And again, up to you whether you go with the first or second in each pair. I like the second a little better, but it really is your call. So in a moment, I'm going to move back to the slides, and then we'll talk about the second type here. I do want to point out, this does leave you with a question when you're talking about significant data, because you don't know where the difference was, right? There's 3 categories. So if you just had 2 categories, it's easy. That's the differences between those 2. But 3, the difference, you don't know which one. Sorry, let me say that again. Back that up. So whenever you have a significant difference, you don't know if it's where that difference lies with a chi-square. Which category was actually the significant one? Significantly different between the observed and the expected. We can take a guess by looking at the residuals, but we just simply don't know. Now, I won't ask you to follow up for this class. Again, for this, I won't ask you to follow up. However, for if you're interested in following up, there are some ways to do it, and I will show you how to follow up on this sort of thing when we talk about the independence test. So there is some potential follow-up that could be done with the independence test. For here, I'm not going to ask you to follow up, but the way, one way to do it is to run follow-up chi-squares. Okay, so that's a possibility, and you could do that, but even that's a bit iffy, actually. So I will just say you don't need to follow up. Okay, if you get the significance, you're done. Or not significance, you're done. Okay, back to the slides. We don't have many more. Okay. So that was our layered. Now here's our second situation, the chi-square test for independence. The 2 qualitative variables, remember? 2 this time, and you want to know if they're independent of each other. And this can be a 2 by 2, a 3 by 4, a 5 by 6, anything you like there, okay? Just as long as you only have 2 variables. And we talked about the example of is gender independent of disorder diagnosed. What are the assumptions here? Very, very similar. 2 categorical variables, should be nominal, honestly, but if you really want it to be ordinal, you got to treat that ordinal as nominal. Next, independence of observations. Persons or cases cannot be in more than one group. Okay. Number 3, this one's a little bit different. The null hypothesis being tested using chi-square test of independence in this guide cannot be used with all types of sampling, not all types of study design. What they're getting at is that this works a little better for cross-sectional than for retrospective or prospective designs. But I feel like that's a topic for really for next semester, in some ways, when we'll talk about that kind of thing. So I don't want you to really worry about assumption 3 too much, and that's why I have it in italics. In other words, I won't ask you to test that assumption. You should basically be aware of it and assume it's true. Okay. All right. And then assumption 4, which is the same we had also dealt with before, which is all cell counts should have expected counts greater than 5. Okay. Back to Laird. Let's go to it. Okay. And good. So I'm actually back to my chi-square test for goodness of fit. I'm going to show you where the next one is. And it's located chi-square test of independence R by C. So first column, 2/3 of the way down, maybe. Just remember chi-square test of independence. Okay. Okay. And we are going to jump ahead to our example here. Oh, yes, this one's a good one. A large real estate agency wants to determine if there's an association between the type of buyer who purchases a property and the type of property that is purchased. As such, a total of 333 buyers were randomly sampled from all the estate agents' clients who bought a property during the past 12 months. The buyers are sorted into 4 categories: single male, single female, married couple, and family. Okay. The type of property these buyers purchased were sorted into 4 categories: flat, bungalow, which is a 1-story home, a detached house, and a terrace, which is a block of adjoining houses common in the United Kingdom. These reflect the categories of our nominal variable buyer type and our nominal variable property type, respectively. Okay. So we've got 4, right? These 4 categories by 4. These 4 categories. Okay. So alternative, the buyer type and the property type are not independent. That is right, are not independent, yes. And the null is that they are independent. Okay. I actually prefer, I think that wording's a little bit confusing, actually. I just tripped over it myself. I prefer this other wording. There is an association between buyer type and property type, or there is no association between buyer type and property type. I think that's a little bit nicer. I know this is the test of independence, but I like that wording a little bit better. Okay, moving on. Now for this, you can do the same setup with the frequencies and the weights that we did for the other one. And I want to show you how that works. So you could have the individual where you write out flat, single male, 40 times. Then flat, single female, 30 times. That's kind of getting more painful as we get to 333 cases. So I recommend you do this method. Remember, there's 4 buyer types by 4 property types, which means we're going to have 16 rows here. 4 times 4, 16. Okay. So we have the flat for the single male, 40 frequency, flat for the single female, 30, flat for the married couple, 16, flat for the family, 10. Then we go on to bungalow, doing those same 4 types again. Detached house with the same 4 types. And terrace with the same 4 types. Okay, each time putting in our frequencies. Okay. So I'll just be really brief because we just looked at this, but this is basically how it would look if you did just put each case in by itself. Remember to put in those value labels. Very important. And that's how it would look. If you weighted it, if you're going to weight it, then you have this additional variable called frequency. First two are nominal. The third one, the frequency is scale, using none for the roll. Okay. Remember those value labels. Okay. And then this is what your data would look like. And then what do we have to do? Same thing. We're going to weight our cases. So we go under data, go under weight. What are we weighting by? Weight cases by frequency. Weight cases by frequency. You can also call it count. You can also call it spaghetti. It really doesn't matter what you call it, as long as you know that that is your count or frequency for this data. Okay, all right. Let's go to the procedure. This time we're going to go to descriptive statistics crosstabs. Descriptive statistics crosstabs. And now we're given a row and a column. So we're going to put property type by the row, buyer type by the column. Could you do the opposite? Yuppers, you could do it whichever way you like. It really doesn't matter. Okay. And again, if you have a frequency, just leave that behind. Just bring over the buyer type and the property type. And we're going to check off a few things. We're going to check off chi-square. Sorry, I should go back a step just to show you where this is. Under statistics, we're going to check off a few things, okay? So you would go here, you put that in there. First, you're going to check statistics. Then you're going to check off the chi-square, the phi and Kramer's V. Then we're going to click continue. Then we're going to go to cells. Remember to check off observed, expected, and adjusted standardized residual. Observed, expected, row and column, and adjusted standardized residual. Okay. This says to round cell counts. Personally, I usually do no adjustments. I don't really like rounding my cell counts, but it's perfectly fine. It's perfectly fine for this class. Okay. Okay. Here are our assumptions again, but we talked these through already, right? The only one we really have to worry about when we run our procedure is the cell count. And you can see they go through and they're looking at each of their expected very diligently, looking for a number less than 5. I don't see any. The lowest number I see is a 6.5. But you don't have to be so diligent because it's going to tell you right here. 0 cells have expected counts less than 5. The minimum expected cell count is 6.5. Now we got some choices here. We're going to look at the Pearson chi-square, the top choice. And I think it's going to show you that in just a second. So no, it's not. Okay, not surprising. We're going to look at the chi-square, the Pearson chi-square, DF of 9. Remember, whenever it's 0.000, how do we report that? P less than 0.001. P less than 0.001. Okay, now we move on to our interpretation of results. We start off with our crosstabs, which is this very nice table. Gives us a lot of good information. Okay. Within each cell, you can see we're getting our observed count, 40, expected count, 19.6, percent within buyer type, percent within property type, and adjusted residual of 6.1. So if you look at percent within buyer type, this plus this plus this plus this equals 100. If you look at percent within property type, this plus this plus this plus this equals 100. Okay, so the 41.7 plus the 31.3 plus the 16.7 plus the 10.4 gives you 100%. Okay, so that's what they mean by the column percent and the row percent. All right. We have our observed counts here, our expected counts, still observed counts here, excuse me. And we just talked through the proportions and percentages. You can compare your observed and expected counts, just like they're doing here. You can also do that by looking at your standardized residual. So here, I guess, yeah, they were taking the long way to get there, but they did get there. The Pearson chi-square test is shown here. Here's our p-value. And the Kramer's V is going to be the choice measure of association. That's our effect size that we're going to look at. So in this case, it's 0.287, which is right around a medium effect size based on this chart. Okay. All right. Now I promised you that we could do some post hocs this time, so we're going to. Don't worry, it's actually pretty straightforward. We're going to look at our adjusted residuals for those that are higher than +3 or lower than -3. Okay, we're looking for something bigger than 3. And what they do is they actually pull together this nice table of observed frequencies with the residuals. It's very nice. Is it necessary? No, I don't think so. I think that's creating a little bit extra. If this was your dissertation, and I know I say that a lot, but if this was your dissertation, yes, you should do it. But for just reporting results for this class, I don't think you need to go there. I would go ahead and take the initial table that it gives you and report that in the results by copying and pasting it. All right. Okay. And then we get to reporting. So let's switch over to APA. And here is for a significant one. A chi-square test of independence was conducted between buyer type and type of property purchased. All expected cell frequencies were greater than 5. There was a statistically significant association between buyer type and type of property purchased. Here we have our chi-square of 9 equals 82.50, p less than 0.001. The association was moderately strong with according to Cohen, with a Kramer's V of 0.287. And then I would put my table here. And you can report, excuse me, any numbers or percentages from the cross tabulation table that you feel appropriate to explain your results, including the adjusted standardized residuals that explain which cells deviated from independence. So I would add a sentence or two here just saying which ones deviated. If it's a whole bunch, maybe I would highlight them as opposed to talking about them. I see it's a number here, but still might be worth just highlighting in a sentence, okay? Okay. Non-significant. A chi-square test of independence was conducted between buyer type and type of property purchased. All expected sell frequencies were greater than 5. There was no statistically significant association between buyer type and type of property purchased with the chi-square. The association was small. There you go. They give the cross tabulation again, although they only give expected this time. Okay. So that's it. It's a pretty short one, as you can see, in terms of the write-up. I would, like I said, I would probably add that sentence in to talk about which ones are significantly different than an independent. So in this case, it would be single males purchasing a flat was higher. Single females purchasing a flat was higher than expected. Married couples purchasing a flat was lower than expected. Families purchasing a flat was lower than expected. You get the idea? I wouldn't talk about these because these are all non-significant. This one's significant, so you could talk about that. None of this one's significant, and this one's significant, and this one's significant. That's kind of a lot for a 4x4, but again, I think if you can knock it out in a sentence or two, it's worth it. If you really feel like it's too much, you can do the highlighting thing. Okay. We didn't talk about one thing, so I'm going back for a second. Not two assumptions, sorry. It's not really where I wanted to go. Oh, here it is. What if you, in this case, what if you get expected sell frequencies that are less than 5? Again, you can collapse some of your categories. You can run your analysis anyway with caution, or you can run an exact test, which requires the SPSS statistics exact module. But again, for our purposes, I would just ask that you run it with caution. Okay. I think you actually have the exact module if you purchase the version that we talked about. But like I said, don't worry about it. Just go ahead and interpret with caution. And I guess you're probably wondering what that means. I would just say in the results, these results should be interpreted with caution because since expected sell frequencies were lower than 5 for this many cells, however many cells it happened for. Okay. All right. Back to our slides one more time. Here we are. And this is our last slide, guys. So I promise you I want to talk about other types of regression. And I do want to go through this just a little bit because I want you to have a sense of what you should do if you run, because regression is a very popular type of analysis to run. And I do want you to know what you should do if you have one of these kinds of situations. Now, dichotomous. In other words, if your dependent variable, your DV, is dichotomous, as opposed to being continuous, which it was for the simple linear and the multiple linear regression, you should consider a logistic regression. Okay. So funny we should be getting here, because really, let's imagine for a second that we had our property type, but let's pretend for a second we only had 2 property types. House, no house. Make it super simple. And then we had our buyer type, which we can keep the same as those 4 categories. As opposed to doing that with a chi-square, we could technically do that with a logistic regression. Be slightly more painful to do that, but we could. Especially if you have a 2 by 2, as opposed to an R by C, then you could do it with logistic regression. But you got to have a dependent variable that's dichotomous of this. But let's suppose we had that previous situation where we have a nominal with more than 2 categories, like the the flat and the terrace and the house and the whatever it was, then you can use a multinomial regression. Then you can use a multinomial regression. So logistic regression could be trying to look at predictors of high suicidality versus low suicidality. Right? Trying to find predictors of that. And you might have some continuous predictors, or you might have, and those should probably be interval or ratio, or you can have nominal predictors. Okay? Either of those are fine. Ordinal are a little funny, but any of the others are fine. The next one, as I just talked about, was multinomial, and that's when you have a nominal with more than two categories. So let me give you an example there. Let's say you're trying to look at mental health service type. And that could be, we'll say, through a mental health professional, through a primary care physician, or trying to come up with a third grouping, or through a caseworker. Let's not make it a caseworker, or through a friend or family member. There you go. So mental health professional, primary care physician, friend or family member. That's who they're receiving their mental health services through. And let's say we wanted to see what the likelihood was based on gender, socioeconomic status, and severity of symptoms. That would be a lovely multinomial regression. Okay. Ordinal regression. That's when your DV is ordinal. I want to predict who will finish in what place of a race, based on hydration beforehand, carbs beforehand, and confidence. Okay, there you go. There's an ordinal regression for you. And finally, count. Count is when you would do a Poisson regression or a negative binomial regression, and both of these can be zero inflated. Okay, so let's talk about this. Let's talk about the number of times a person goes to therapy, mental health therapy, number of visits they make, and our predictor could be the severity of illness. We could have several predictors. We could have gender, we could have, again, socioeconomic status if you like, and but let's put in mental health symptom severity. Okay. And then we're predicting how many times that they actually went to a mental health therapist. Now, if we are, since we know that most people with symptoms don't actually show up in mental health therapy, or at least a large number don't, that's where you can have a zero inflated, because for a lot of people, the answer may be zero. So that zero gets large, okay? So there's all kind of fun things you can do with that too. But I just want you to be aware of these different types of regression out there, what they mean, and where they might apply, okay? And so that's all I want to say for today. I look forward to speaking with you in class. In the meantime, stay safe and be well, and I'll talk to you later.